is the notes for AP Calculus on the topic of limits at infinity, horizontal asymptotes. So remember, if you have the limit as x approaches infinity of a function, f of x, it's the value of the function as x increases without bounds. So there you would look as far right on the graph as the graph goes. The limit as x approaches infinity. And the possible things you could get, the graph could keep going up forever, in which case the limit would be infinity. It could keep going down forever, in which case the limit would be negative infinity, or it could level off at some horizontal asymptote, y equals some constant, and then c, that constant would be your limit as x approaches infinity. So it would get closer and closer to it like that. Similarly, if you're finding the limit as x approaches negative infinity, it's the value of the function approaches as x decreases without bounds. So there you look as far left on the graph as it goes. So the limit as x approaches negative infinity. Again, you have the same options. It could go up to infinity. It could keep going down forever to negative infinity. Or again, somewhere you could have some horizontal asymptote, y equals c, and you could approach that, and so then your limit would be c. Or the other possibility on both sides is the function might not even head to infinity or negative infinity, in which case it would be does not exist. All right, let's look at some specific examples here. So we start off similar to other limits when x is approaching a specific value. What you can do first to help you analyze it is first substitute in what x is approaching, in this case negative infinity. So we have negative infinity cubed minus 2 times negative infinity squared plus 3 over negative infinity squared plus 4 times negative infinity. And then to analyze it from there, well, let's start with the numerator. We've got negative infinity cubed, that's some huge negative number. We've got negative infinity squared times 2, negative 2, and then we've got plus 3. So with these infinities here, this plus 3 is so much smaller than it that it's pretty much negligible and we can ignore it when we're evaluating our limits. And then on the numerator, we negative infinity cubed and negative infinity squared. Those are both huge, huge numbers. However, because the exponent 3 is bigger than the exponent here 2, even though negative infinity squared creates some huge number, negative infinity cubed is so much larger in magnitude that even this term, the negative 2, negative infinity squared, is negligible compared to the size of negative infinity cubed. So the only thing that's going to matter on the numerator is the negative infinity cubed. Similarly, on the denominator, we've got 4 times negative infinity, which is a huge number, but negative infinity squared in magnitude is even larger because it has a larger exponent. So this one's negligible. So when you have polynomials like this, you just use the terms with the highest exponents on the numerator and denominator. So what we have left now is negative infinity cubed over negative infinity squared. And then we can simplify it from there. Whoops. So similar to how you would simplify if these were x's, we have negative infinity squared reduces that, and you're left with a 1 on the numerator. So now you have negative infinity over, we still have this negative 1 out front, over negative 1. Negative infinity divided by negative 1 gives you positive infinity. So what that tells you is the graph goes to negative infinity, it goes up to infinity. So it would look like this. So x approaches negative infinity, it's going up to infinity. Now let's look at the same function for x approaches positive infinity. And now that we know it's the term with the highest exponent on the polynomials that matters, we can use that shortcut and rather than plugging infinity into everything. So this would be the numerator, highest exponent is 3, so it would be infinity cubed over negative infinity squared. And again, you can see 2 of those reduce out, so we're left with infinity over negative 1. This time that's going to be negative infinity. So that means as x approaches infinity, the function approaches negative infinity, so it looks like this. X goes to infinity over here, it's heading to negative, so it would be heading down on this end of the graph. Now let's take a look as x approaches negative infinity on this one. So we've got the square root of x squared plus 5. Again, even though it's in the square root of x squared, when you plug in infinity, it's going to be a much larger magnitude than the 5, so the 5 is basically negligible. So on the numerator, we've got negative infinity squared squared. And notice every time I substitute negative infinity, I put it in parentheses. Whereas infinity, you don't have to worry about that. Over on the denominator, this exponent 1, so the negative 4 is going to be much smaller when you substitute in infinity or negative infinity, so that's negligible. So it'd be 3 times negative infinity. But here's where we got to be a little bit careful here. It's tempting to just cancel out the square root and the squared there, but that would actually give you the wrong answer. Because what would happen first is actually you'd square the negative infinity. And when you square a negative number, it becomes positive. And then on the denominator, 3 times negative infinity, you can just move that negative out in front, so it'd be negative 3 times infinity. And now the square root of infinity squared, that's just going to be infinity over negative 3 times infinity. So this time, notice what happens, the infinities completely reduce out, and what we're left with is negative 1/3. So that is your limit. So when you get a specific number like that, that indicates that it must be leveling and off, approaching that number, so we must have a horizontal asymptote. Well, horizontal line is just y equals, so it would just be y equals negative 1/3. Now let's try the same function with infinity. So if we substitute an infinity in the numerator, again the x squared would be what matters, has a higher exponent, but it's still inside the square root, over 3 times infinity. So the square root of infinity squared is infinity over 3 times infinity. Again, you can see the infinity is completely reduced out. So we're left with 1/3. So again, we have a specific constant there. It's not infinity or negative infinity. So what that indicates is you have a horizontal asymptote. I've just abbreviated here. It's not an official abbreviation, but just for our notes purposes to save room. So horizontal asymptote at y equals 1/3. So this function right here has 2 horizontal asymptotes. On the left, as x approaches negative infinity, it's got a horizontal asymptote of y equals negative 1/3. And as x approaches infinity, it's got another different horizontal asymptote of y equals 1/3. And that's the most any function can have, is 2 horizontal asymptotes. If we have 2, we could have 1, or like the first example we did, we could have none. Let's take a look at the next example. On the numerator here, what's going to matter with the term with the highest exponent of the polynomial, so that'd be 4 infinity squared. And the denominator, it'd be negative 5 infinity cubed. So then you can see to reduce that out, infinity left on the denominator, so we'll have 4 over negative 5 times infinity. Well, just think about this. This is 4 over some huge negative number. What's that really close to? Well, 4 over some huge negative number is just going to get really, really close to 0. So that is what the limit is. So the horizontal asymptote here will just be right on the x-axis. The equation y equals 0. Again, anytime you get a constant there that's not infinity or negative infinity, that indicates you have a horizontal asymptote. All right, let's take a look at this one. We have negative infinity. On the numerator, we'll have 3 negative infinity to the 4th. Over on the denominator, negative 2 negative infinity to the 4th. So you can see those completely reduce out. So we're left with negative 3/2. Is our limit. And again, we have a constant there, so that indicates we have a horizontal asymptote of y equals negative 3/2. So if you're ever asked to find horizontal asymptotes, this is how you do it. You find the limits as x approaches infinity and negative infinity. And if you get specific numbers like these, that indicates the presence of a horizontal asymptote. Now let's take a look at the next one here. We've got some fractional exponents. Let's try infinity first. Remember, square root of x, that's like a 2 there and a 1 there. That's the same as x to the 1/2. So you can apply the same principle we used with the polynomials. We can look at the term with the highest exponent. So we've got x to the 4/7 versus x to the 1/2. 4/7 is a little more than 1/2. So on the numerator, what's going to matter is 4 infinity to the 4/7. And the denominator, we've got x to the 1/3 versus x to the 3/4. So 3/4 is bigger, and it's negative part of that term, so it's going to be negative infinity to the 3/4 on the denominator. But on this one, in order to see how it reduces, what you want to do is get a common denominator. the two fractional exponents. So, common number of 4 and 7 would be 28, so we can make this one over 28. Multiply by 4 over 4, that'd be 16 over 28. And the denominator, we have the negative, and then this would be infinity to the, if we multiply by 7 over 7, that'd be 21 over 28. So you can see what you do with the exponents, remember, just like we did here, like 3 minus 2 is 1, you subtract them. So it'd be 4, which we completely reduce out, and 21 28ths minus 16 28ths would give you 5 28ths. So even though that's a fractional exponent, it'd be the 5th root of infinity, sorry, the 28th root of infinity to the 5th power, because it's on the denominator, that's still huge compared to 4, so this is going to approach 0. So whenever you have infinities left over on the denominator, it's always going to be 0. So we have a horizontal asymptote of y equals 1. Now let's try negative. Again, negative infinity, you usually have to be a little bit more careful on a lot of these as opposed to positive infinity. So if we try to do the same thing, if we went 4 negative infinity to the 4/7 over negative infinity to the 3/4, and try to work it out the same way, you'd probably get 0 again. However, you have to remember these fractional exponents represent radicals, and this is a negative infinity, a huge negative number. So think about what would happen if you substitute a huge negative number into a square root, or any negative number would give you an imaginary number, right? So this one would not exist, and same thing here. This is a 4th root, so this would also not exist. So because of this one's like a square root, right? And this is the 4th root of x cubed. Okay. Even roots, when we have negative infinity inside, call this n, if n is even. Then your answer is going to be does not exist. Because you can't have a negative number inside even root and get a real answer, so you always imaginary. Okay, let's take a look at a few more here. On this one, let's substitute infinity. So in the numerator, what's going to matter is that it's negative infinity to the 5th, and the denominator negative 4 infinity to the 5th. So here the infinities completely cancel, reduce out, and we're left with negative 1 over negative 4 gives you 1/4. Again, we have a specific number here, so I have a horizontal asymptote of y equals 1/4. Now let's try the next one. We've got sine x over x squared minus 7. So if we have sine of infinity over infinity squared is what's going to matter in the denominator. Well, here you want to think about what the graph of sine looks like. So, if you remember, the graph of sine basically goes between negative 1 and 1. And it goes like this, to 1, down to negative 1, to 1, down to negative 1. And so it keeps on going forever. Fluctuates back and forth between 1 and negative 1. So, the numerator is going back and forth between 1 and negative 1. Meanwhile, the denominator is huge. It's infinity squared. So whenever the denominator is that much larger than the numerator, this is going to approach 0. So this one does have a horizontal asymptote of y equals 0. What this would look like graphically is something like this. Because the denominator keeps getting bigger, the values get smaller as we go. So it's going to keep fluctuating back and forth between positive and negative because the denominator is just positive. But because the denominator gets bigger and bigger, those fluctuations get smaller and smaller. So one of the common misconceptions about horizontal asymptotes is that they are never crossed. But that is not true. Horizontal asymptotes can be crossed. As we can see, this one gets crossed several times, the y equals 0. It's the vertical asymptotes that are never crossed. Horizontal ones can actually be crossed. Sometimes they are. All right, let's take a look at the next one. Notice this one's in the first one we encountered this in factored form. So you could multiply it all out if you want. That would work. However, remember this is going to turn into two polynomials when you do that. So really all you have to worry about is the terms that end up having the highest exponent. So if you look on the numerator, the x squared times x is going to give you x cubed. That's going to be the highest exponent that matters on the numerator. And on the denominator, if we first multiply these together, you can see the highest exponent here with those binomials would be negative 3x squared. But then it's also multiplied by the x on the outside there, so that's going to make it negative 3x cubed. So even though you could multiply it out and write all the terms, we know those are the only terms that are going to matter when we plug in infinity or negative infinity. So now we substitute in negative infinity cubed over negative 3 times negative infinity cubed. And you can see the negative infinity cubed is reduced out, so you're just left with negative 1/3. And since we got a specific value again, this one would have a horizontal asymptote of y equals negative 1/3. All right, now let's take a look at this one. If we plug in infinity, now here we've got exponential functions in here as part of this. We've got 3 minus 2 to the infinity over 5 plus 2 to the infinity. So these are not polynomials, they've got some exponential ones in there. Polynomials just have constants as their exponents. Here the x is up in the exponent. So here, what do you think is going to matter? 2 to the infinity versus 3. Well, 2 to the infinity is 2 times 2 times 2 forever. So that's going to be much larger than 3, so the 3 is negligible. Same thing on the denominator. 2 to the infinity is much larger than 5, so that's negligible. So we have negative 2 infinity over 2 to the infinity, that's what's left. And you can see those reduce out, so all that's left is negative 1. So this one will have a horizontal asymptote of y equals negative 1. So now let's look at negative infinity. Again, you always got to be a little more careful with negative infinity. So you've got 3 minus 2 to the negative infinity over 5 plus 2 to the negative infinity. So oftentimes a mistake is made by assuming, oh yeah, the 3 and the 5 are again going to be negligible. But let's take a look at what happens because these are negative exponents. Now because of this 3 and 5, we can't just move these to the numerator and denominator. Because there's other terms that are not in factored form. So what we can do though is rewrite each one. This is 3 minus, instead of 2 to the negative infinity, that's the same as 1 over 2 to the infinity. And here we got 5 plus 1 over 2 to the infinity. And now take a look. What's 1 over 2 to the infinity really close to? Okay. That's basically 0, right? 1 over some huge number, same thing here. So 0 compared with 3 and 5, now the 3 and the 5 are really what matters. So we get 3/5 is our limit, and that means we have a horizontal asymptote of y equals 3/5. Let's take a look at a few more here. On this one, if you substitute infinity, on the numerator it's going to be negative 3 infinity to the 4th over 4 infinity cubed. So you can see 3 of those reduce out, and you with 1. So we have negative 3 infinity over 4. But does that seem like an appropriate answer, negative 3 infinity over 4? No. Well, if there's infinities left on the numerator, then your answer is either going to be a big positive number or a big negative number. In this case, it's a big negative number, so your answer is negative infinity. And there's no horizontal asymptote with either infinity or negative infinity. On this one, if we substitute in negative infinity now, we'll have negative 3, negative infinity to the 4th, over 4 times negative infinity cubed. So those negative infinity cubed reduces out, leaving you with 1, which is important, because if you have negative infinity to the first, or just negative infinity times a negative 3, it's going to make it a positive 3 times infinity over 4. So this time with infinity is left on the numerator, it's going to be a big positive number, giving you positive infinity. Let's take a look at another one with fractional exponents. Here we've got x to the 1/4 versus x to the 2/3. So 2/3 is bigger, so it's going to be infinity to the 2/3 And here we've got x to the 1/4 versus x to the 2/5. 2/5 is bigger, so that's going to be 3 infinity to the 2/5. And again, you can just get a common denominator here. 15, so that'd be infinity multiplied by 5/5, that'd be 10/15 over 3 times infinity multiplied by 3 to the 6/15. So when you subtract the exponents, we get infinity 10/15 minus 6/15 is to the 4/15 over 3. Okay. Again, all we're concerned with is whether this is positive or negative, because we have infinity left on the numerator. And you can see it's positive, so it's going to be a big positive number. Oops, it'll be positive. Notice this exponent in this case, because it's infinity, doesn't matter in terms of whether it's even or odd. But if this had been a negative infinity to this power, that would actually affect it, because the odd root would make the 15th root of a negative infinity would be negative, and then when you raise it to the 4th power, that's going to make it the even root. So it's even power, so it's going to be a positive. So that's what exactly how many are left over can sometimes matter. All right, let's take a look at the next one. On this one, if we substitute infinity, we have cosine of 1 over infinity. Well, what's 1 over infinity really close to? 1 over some huge number? Really close to 0. So that's about 0. And then what's the cosine of 0? The cosine of 0 is 1. Let's take a look at the next one. As x approaches infinity, on the numerator, we can see we have infinity to the 10th. That's a polynomial, but on the denominator, it's an exponential one. E to the infinity. So, the question is, we can't just reduce it out. The question is, which of those is going to be larger? Infinity to the 10th over e to the infinity. And the way to think about this, there would be infinity to the 10th would be 10 infinities multiplied together. Yeah, so there's 10 of them. Okay. Versus e to the infinity, remember, means e is approximately 2.71. So e to the infinity means we've got e times e times e times e times e times e. But this time, it's to the infinite power, right? So it does not have an end to it. So because that one doesn't have an end to it, it keeps on going forever, versus this one does have an end, there's just 10 of them. Eventually, this one's going to get much, much bigger. And since the denominator is much larger than the numerator, whenever that's the case, it's going to be 0. Here's your answer. So then more asymptote of y equals 0. But now let's look at negative infinity. And negative infinity can be a little different. So we plug in negative infinity, we have negative infinity to the 10th over e to the negative infinity. So negative infinity to the 10th, that's an even power, right? So it's going to make it a positive infinity to the 10th. And this time, since that's the only term in the denominator, we can move it up to be a positive exponent and be e to the positive infinity up there. And there's nothing left on the denominator, so we've got a huge positive number times another huge positive number. That's going to be infinity. And that one doesn't have a horizontal stroke on that side. And that concludes the notes for AP Calculus on the topic of limits at infinity, which tells you how to find horizontal